theory work. The other, slight digression, but in fact, Newton thought about a cosmological constant as well. Because if you look at Newtonian gravity, one of the major features of Newtonian gravity that makes it possible to calculate things in realistic situations is Newton's famous field theorem, which basically says that if I had two spherical masses here, and I want to calculate the total gravitational force between them, so this one has total mass m, this small m, then I can calculate the total gravitational force between them by just replacing these extended spheres here by point masses of the same mass as the original spheres, but located at the centers. So Newtonian gravity has this simple feature. And the force law of Newton says that the force depends on the distance, the inverse square of the distance between the centers. Now, one question one can ask is whether whether there are other force laws which gives you the same behavior, whether there are other mathematical forms of this law which allows you to replace extended spherical mass distributions by point masses. And the answer is that Newton knew this, that you can also add a term which is proportional to R. And it turns out that this will behave exactly like a cosmological constant. So in some sense, there is a cosmological constant in Newtonian theory as well. But that's a digression. Anyway, the model of the universe Einstein came up with then was sort of like the surface of a sphere. Like it was obviously at 3 spatial dimensions, but if you take away one of them, you can think about it as the surface of the Earth, basically. So it was a universe which was static, it had finite volume, but there was no beginning or end. And it was possible to, you can start off at one point, travel in what you think is a straight line, and if you travel long enough, you get back where you started. But it had one feature which made it unworkable even in theory, and that is that it's unstable. If you have a model like the Einstein universe, and you just introduce a slight variation in the density somewhere, but you assume that the density was constant. And it only balances at a certain value of the density as well. So if you increase the density ever so slightly, and just introduce an inhomogeneity somewhere, then the universe will either collapse or expand. And that's why recently when I thought about this, it struck me that this would have been a good universe for a creator to make. Because if he had discovered that, the universe is described by the Einstein model, then, such a universe would need constant intervention just to be there. Then we could really see that would at least make it, in some sense, more possible that there was something or someone who made sure that the universe didn't collapse instantly. So if the universe had been created, then the model of choice should have been the Einstein model. Okay, so one thing which is extremely important in astronomy and cosmology is measuring distances. Like I said, when Einstein formulated his model, they they had no idea that there were galaxies beside the Milky Way. And the problem was that it was, and still is to a large extent, difficult to measure distances in the universe. And we have sort of developed over many years a mesh of different techniques which to some extent overlap, and we have to rely on in order to establish the cosmic distance scale. So for the closest stars, we can just use geometric parallax, like when you look at an object from the sun here and the Earth's orbit here, then let's say at opposite times of the year, a star out here, which is very close, the distant stars out here, this star will appear to be moving with respect to the distant stars. So we can measure this angle, and then since we know the dimensions of Earth's orbit, we can calculate the distance to this star. So that's parallax here. But I mean, these angles rapidly become extremely small, and it wasn't until the early 1800s that one was able to measure a parallax for the first time. So today we've been able to use that technique out to about 150 parsecs, or something like 400 or 500 light years. Still, on the local objects within the Milky Way. Then I'm not going to go through all these techniques, but on cosmological scales, when we're talking about millions and billions of light years, then there are two important techniques, namely using variable stars and using supernovae of a certain kind. And the whole idea of using these objects to measure distances is very simple. I mean, if you have a light bulb and you know how many watts it is, then you can tell how far away it is just by measuring how many photons you receive from it per second. Because the far further away it is, the lower the flux will be. And the flux will vary with the distance in like 1 of the square of the distance. So like 1 over the distance, like 1 square would say.
Yes. Thank you.
So we have an object which radiates here, and then its radiation, as it moves out into the universe, is spread evenly out of this sphere. And if you know how many photons per second you receive, you can calculate how far away the source is, if you know the strength of the source. So if you have objects which we call standard candles, basically know how many watts they are, then we can, by measuring how many photons we collect in our telescopes here on Earth, we can calculate how far away they are. And one important class of objects where we do know something about their intrinsic brightness are the Cepheid variables. And they come in two types. These are stars which have left the main sequence. I mean, they have finished their hydrogen burning phase and go through a period where they oscillate. And they oscillate was discovered that they oscillate in a very systematic way, so that their intrinsic brightness and the period of the oscillations are tightly connected. There are two main classes of Cepheids which have caused some trouble from time to time, but anyway, if you can measure the period of these variations, and that's not too difficult to do, then you can say something about their very intrinsic brightness, or how many watts they are. And the first one to use this technique to discover that there are objects outside of the